The objective of this lecture is to study orientation of a rigid body using Euler angles. So we're going to parameterize the orientation of a rigid body using a set of angles which are defined as Euler angles, and of course I'll get into that as we go through the lecture. But the starting point is as follows, is let B be a rigid body. And let A be an arbitrary reference frame. Suppose that B translates and rotates relative to A. And furthermore, let O be a point fixed in A, and let C be the center of mass of B. And finally, I'm going to define it as E equals E1, E2, E3 be a basis fixed in B. Now, the way this picture looks, it's the standard picture, but we're going to do some things to it that are a little different from what we've done before with kinematics. Is here we have a frame A, and we have a point O, and O is fixed in A. And then we have a rigid body, B, and we have the center of mass of B, which is a point which I'm going to define as C. And then we have a basis, and that basis I'm going to define as E1, E2, and E3, and then there's this point C. So the point C, together with the basis E1, E2, E3, is fixed in B. So that whole thing is fixed in B. Now, from kinematics, we know that the angular velocity of B and A has the form. So we always write this now, the angular velocity of B and A, as a linear combination of components in the body fixed basis, right? This is the way we've, when we do the transport theorem, we always write everything in terms of the last rotating frame. That frame in this case that we're interested in is the rigid body itself. Now, what's important about this is that this angular velocity is not the rate of change of some other vector. This is a very important point with regard to rotations, which doesn't apply to translations, is that the angular velocity of B and A is, in general, not the rate of change of some other vector. In other words, there doesn't exist a vector such that when I take its rate of change, I get the angular velocity. So I could write it that way. So in other words, in general, there does not exist a vector, which I'll define as capital theta, such that the rate of change in either frame, let's say an A, of theta is equal to omega BA. So I'm going to make this here. This is not in general true. Not true in general. So as a result of it not being true in general, you can't find three quantities, call them theta 1, theta 2, and theta 3, or whatever you want to call them, say Q1, Q2, Q3, such that their rates of change are equal to omega 1, omega 2, omega 3. So that, let's write that down. So therefore, in general, there do not exist three quantities let's call them Q1, Q2, and Q3, such that Q1 dot, or I just say QI dot, QI dot is equal to omega I. Again, this is not true in general. That doesn't mean that there may not be specific cases for which it is true. It means that in general it's not true. So as a result, we have to parameterize the angular velocity a different way. So because of the aforementioned facts, the angular velocity of B and A must be parameterized in a manner different from finding quantities whose rates of change are the components of the angular velocity. Now, one way to do that, it's not the only way to do it, but one way that's commonly done is what's called Euler angles. So a common approach to parameterizing the angular velocity of a body is to use what are called Euler angles. Now, Euler angles, there are, in general, 12 different Euler angle sequences. Euler angles, what they form are a sequence of three successive rotations that provide a description of the orientation of the body, in this case it's the rigid body, B, relative to any reference frame of interest. Now, as I said, there are 12 different sequences of Euler angles. We're going to do one of them. So I'm not going to do all 12 because it's a little beyond the scope of this lecture. So while there exist 12 different Euler angle sequences, in this study, the focus will be on the what are called 3, 2, 1 Euler angles. Now, I'm going to draw some pictures first, and then we'll get each of these Euler angles together. First, I'm going to start with the three-dimensional picture. I'm going to draw the full three-dimensional picture, and then we're going to break it down into 2 dimensions. So there are 3 rotations. So because there are 3, they said there are 3 successive rotations. The first rotation is going to be defined by an angle, and I'm going to call that angle psi. And it's about the original, and I'm going to put it in quotes, 3 axis. The second rotation is going to be by an angle theta, and that's going to be about the new 2 axis. What I mean by the new 2 axis is the 2 axis that results from the first rotation, because these are successive rotations. And then the third rotation is going to be by an angle phi about the new 1 axis. Now, the way this is going to work is that, so we're going to start with an orientation. We're going to rotate about the original 3 axis by this angle psi. Then we're going to take that orientation and we're going to rotate by the angle theta about the new 2 axis. Then we're going to take that orientation and then we're going to rotate by the angle phi about the new 1 axis. These rotations look as follows in 3 dimensions. So this takes a little bit of sort of visualization, but this is why I'm going to break it down into pictures which are 2-dimensional when we're all done. So let's start with this frame A again. So all we're dealing with here now is rotation. So we're not dealing with the translation part. So we're just worried about how B rotates relative to A. We're not worried about anything with regard to the translation of the rigid body. The translation is taken care of by the motion of the center of mass, and in this case, we're not concerned with the motion of the center of mass. So now here's how this works. We will start this way. Here's the original orientation of the body, frame A. It's aligned with frame A. I'm going to call these 3 directions, I'm going to call them E1, E2, and E3. E1, E2, E3 is going to be fixed in frame A. The first rotation of the body is about the 3 axis, so you see this E3. So now what I'm going to do is I'm going to start coloring these, and the colors are going to be chosen in such a way that they represent the different rotations. So this first rotation is about this axis, and I'm going to label it, I'm going to call it P3. And I'll explain why I'm calling it P3 in just a second. But here's what it looks like. I do a rotation by the angle psi. So the angle psi is an angle that rotates the basis vectors E1, E2, E3 to give me two new basis vectors. Those two new basis vectors are going to be called P1 and P2. And I'm doing the rotation by an angle psi about the 3-axis. So that's the first rotation. The second rotation, which I'm going to mark in blue, is now starting from this direction P2, because remember it says the second rotation is by an angle theta about the new 2-axis. The new 2-axis is P2 because of the way I've defined the first rotation. The first rotation is about E3, which is equal to P3, and as a result of that I wind up with these two new vectors P1 and P2. I'm going to do the second rotation about the direction P2. So this gives me another set of vectors. Here are the vectors, and the vectors look as follows. So I got to be a little careful with the way I draw this so that I save room for the third rotation. So here's the new set of vectors that result from the second rotation. So this becomes Q3 because I'm rotating about P2. So P2 is also equal to another vector which I'm going to call Q2. I have to give myself enough room here. So let's draw this a little bit differently. Let's move P2 over here, so I give myself enough room to be able to draw Q2. So this direction right here is Q2, and then that makes this direction down here Q1. Now the second rotation is by the angle theta. Then the third rotation is going to be defined by the last angle, which is phi, and it's about the new 1-axis. Notice that the new 1-axis now is Q1, so I'm going to do a rotation, and that's going to give me a third angle, and that third angle is going to be this angle which I'm going to define as phi. And phi I'm going to mark it with green. So here's the third rotation. So there's the angle that defines the third rotation right here. This angle is phi, and I'm doing the rotation about Q1. This direction here then becomes E3, which is fixed in the body fixed basis, and then this direction here, Q2, gets rotated to a new direction, which I'm going to draw here, which is going to be E2, and then the rotation takes place. So this angle here becomes the rotation takes place about this axis. So this angle here is the angle phi, and then this direction right here, Q1, is equal to E1. Now, of course, if you look at that, you'll say, well, that's a little hard to see because it's in 3 dimensions. It is true. It is hard to see. It's in 3 dimensions. Let's go through and do these now as a series of 2-dimensional pictures. So here's rotation 1. So rotation 1 looks like this. This is by the angle psi about E3 equals P3. So if I look at that, and if I look down on the picture, here's what it looks like. Here's E3, which is also equal to P3. These two directions are E1 and E2. Now remember that they're fixed in frame A. This right here is the sequence, or the first angle in the sequence that is this angle psi. And to make this a little clearer, let's make this orthogonal. So this angle, this direction here is P1, this direction is P2, and this angle is psi. Now you can see that when you do this, what winds up happening is you have the following, which is that suppose we say that this basis P1, P2, P3, I'm going to say that P1, P2, P3 is fixed in a frame. I'm going to call that frame capital P. I know that E1, E2, E3, as I said originally, is fixed in frame A. So as a result, I know that the angular velocity of P in A is equal to psi dot times P3. Remember, I always write things in terms of the basis that's rotating relative to the other basis, or the frame, sorry, I should say, it's in the basis that's fixed in the frame that's rotating relative to the frame from which I'm measuring. I'm measuring, in this case, from frame A, the rotation by the angle psi to this new basis P1, P2, P3, and P1, P2, P3 is fixed in frame P, so I write this in terms of coordinates that are fixed in frame P. Now, you can also see from this that I get the following result, which is that P1 is equal to cosine of psi times E1 plus the sine of psi times E2. And then I also get that P2 is equal to cosine of psi times E2 and then minus the sine of psi times E1. And as a result of that, I can write the inverse transformation, and the inverse transformation looks like this, which is that E1 is equal to, if you look at it, E1 is equal to cosine of psi times P1, and then minus the sine of psi times P2, and then E2 is equal to cosine of psi times P2, and then plus the sine of psi times P1. So that gives me a way to be able to go back and forth between these, and so that just tells you the relationship between all these. Now let's do rotation 2. So rotation 2 looks like this. Now remember that rotation 2 takes place just like rotation 1 here. Rotation 2 takes place now by the angle theta about the new 2-axis. Which is equal to P2, which is also equal to Q2. So let's draw that picture. All right, so here we go. So what we have now is we're going to start where we left off. Where did we leave off? We left off here with this rotation by the angle psi. Now we're going to do a rotation about the 2-axis, and if you do that, you'll actually see that this picture is actually more effectively drawn the other way, which is that we're going to do P2 is out of the page, and that's equal to Q2. And that's like looking down on the direction P2 in this diagram. So if we do that, then this direction here becomes P1. And so since we're rotating, this direction here becomes P3 because P1 cross P2 is P3. And we get this rotation here by this angle, which I've defined as theta. And the angle theta takes me to this new basis, which is Q3 and then Q1. So if you look at this now, you'll see that this basis again, P1, P2, P3, is fixed in P, and then this new basis, Q1, Q2, Q3, is fixed in Q. So as a result of that, you'll see that the angular velocity of frame Q relative to frame P is equal to theta dot times Q2, where again I'm doing the same thing I did before. Now, maybe, for saving myself a little bit of space, I'll move this over here. We've got omega QP is equal to theta dot times Q2. Now we can write the basis vectors the exact same way. We know that, for completeness over here, just to finish up the discussion here. Here we have P3 equals E3, but I wrote that in the diagram, and I'll put it over here. So now what we've got is we've got Q1 is equal to cosine of theta times P1, and then we've got minus the sine of theta times Q3. We've also got that Q3 is equal to cosine of theta times P3, and then plus the sine of theta times P1. Now, if we write the reverse transformation or the inverse transformation, we have that P1 is equal to cosine of theta times Q1, and then we've got minus the sine of theta plus the sine of theta times Q3, and then we've got P3 is equal to cosine of theta times Q3, and then minus the sine of theta times Q1, and we've got that Q2 equals P2. So now you see we've got these two rotations defined, and everything else is defined too, including that angular velocity. Now we're going to do the third rotation, rotation 3. Rotation 3 is by this angle, which I'm going to call phi, about the new one-axis. Which is equal to, it's the same way it is here, it's equal to Q1, which is also equal to E1. So now let's draw that picture. So if you look here, you'll see that there's the Q1 axis, and now I'm going to look down on that axis, and as a result, I'm going to have Q1 out of the page, but that's also equal to E1. And now we're going to have Q3 in this picture. Q3 is going to be to the left, and then Q2 is going to be up in this diagram. So now we're going to do a rotation by this angle, which I'm going to define as phi, about this direction. So there is E1, and then this is E3. Sorry, this is not Q2. This is Q3. This is Q2. Sorry, Q2, and this is Q3. I'm doing rotation about 1. So this direction here becomes E2, and this becomes E3. E3. And then this angle here is phi, and then this angle here is phi. And now we can do all the same things we did before, which is that we know that Q1, Q2, Q3 is fixed in Q, and we know that this last basis, which is E1, E2, E3, is fixed in the body, which is B. So now what we have is we have a couple of things. We have that the angular velocity of the body as viewed by an observer in Q is equal to phi dot times E1. And now we can write the transformations the same way we did before, which is that we have E2, you can see E2 is equal to cosine of phi times Q2 plus the sine of phi times Q3. And then we have E3 is equal to cosine of phi times Q3, and then we have minus the sine of phi times Q2. And then the reverse or the inverse transformation, we've got Q2 you can see that Q2 is equal to cosine of phi times E2, and then minus the sine of phi times E3, and then we have Q3 is equal to cosine of phi times E3, and then we have plus the sine of phi times E2. And finally, just for completeness, just like we did over here, we have that Q1, or I should say E1, given the order in which I did this. E1 is equal to Q1. Now let's start looking at these and let's start adding them up, which is that we know the angular velocity of B in A has to equal the angular velocity of P in A plus the angular velocity of Q in P plus the angular velocity of B in Q. Well, that's equal to, well, let's go through our sequences here. We've got psi dot times P3 plus theta dot times Q2 plus phi dot times E1. But remember, whenever we do kinematics, we always want to write the angular velocity in terms of the coordinate system fixed in the last rotating frame. The last rotating frame is the body in this case, because that's the frame whose angular velocity we're interested in relative to frame A. So we want to express omega BA in terms of the body fixed basis E equals E1, E2, E3. So in order to be able to do that, we need to use these transformations. So now let's look. You see that Q2, I already have it. Q2 is equal to, in terms of the body fixed basis. So Q2 is equal to, well, it's equal to cosine of phi E2 minus the sine of phi times E3. Right? That takes care of that. Takes care of that last rotation. Now, sorry, the second rotation. So now what we have to do is we have to march through this, and we have to figure out how to get this other part, because you'll notice that I've got P3. So let's look at P3. So you'll see that P3 is equal to minus the sine of theta Q1, there's a plus here, plus the cosine of theta times Q3. So let's write that down. P3 is equal to minus the sine of theta times Q1 plus the cosine of theta times Q3. Now you can see that from that result, we can actually substitute in now. This is equal to minus the sine of theta times Q1. But what's Q1 equal to? Q1 is equal to E1. So this is equal to E1 plus the cosine of theta. So the cosine of theta times Q3. But Q3 is equal to sine of phi E2 plus cosine of phi E3. And now you can see that when we do all that, we wind up with this being written as, let's write it out. We've got minus the sine of theta, E1, plus cosine of theta, sine of phi, E2, and then plus cosine theta, cosine phi times E3. So now what we can do is we can take Q2 and Q3 and we can substitute them, sorry, Q2 and P3 and substitute them in to get omega BA. So therefore, omega BA, when expressed in this body fixed basis, is going to equal psi dot times P3. P3 is minus the sine of theta times E1 plus the cosine of theta times the sine of phi times E2 plus the cosine of theta times the cosine of phi times E3. And then we've got plus theta dot times Q2. Q2 is equal to cosine of phi times E2 minus the sine of phi times E3. And then we have finally plus phi dot times E1. So as a result, now we can simplify. So then omega BA is equal to, well, let's gather all the E1 terms. So we've got phi dot minus psi dot sine theta. This whole thing is multiplied by E1 plus, now the E2 terms. I've got psi dot cosine theta sine phi, and then I have theta dot cosine phi. So psi dot cosine theta sine phi, and then plus theta dot cosine phi. And that's times E2. And then the last one is E3. I've got psi dot cosine theta cosine phi, and then so psi dot cosine theta cosine of phi, and then what else do we have? We've got minus theta dot sine phi. And that's times E3. So this is the angular velocity. So I have to write this. This is the angular velocity of B in A in terms of the Euler angle sequence, say the 3, 2, 1 Euler angle sequence, psi theta phi, expressed in the basis E equals E1, E2, E3, where E is fixed in B. So you can see here that, remember, so recall something. Recall that in general, omega BA is equal to omega 1 E1 plus omega 2 E2 plus omega 3 E3. So as a result of that, you can see that these three quantities, which these omega 1s, so omega I, so omega 1 is equal to psi dot, the phi dot minus psi dot sine theta, and we could see that omega 2 is equal to psi dot cosine theta sine phi plus theta dot cosine phi, and then omega 3 is equal to psi dot cosine theta times the cosine of phi minus theta dot times the sine of phi. And we'll notice something. Observe that omega I, for I equals 1 2, and 3 are not the rates of change of 3 other quantities. Because if you look at these quantities, you'll see that omega 1 is phi dot minus psi dot sine theta. There's no quantity such that when I take its derivative, I get phi dot minus psi dot sine theta. So in general, it's going to be the case. So this goes back to what I said at the beginning. So therefore, in general, there does not exist a vector, which I call theta, such that the rate of change of theta in frame A is equal to omega BA. It does not exist. All right, so now there's one case where this does work, but it's only a special case, and I'm just going to bring it up just parenthetically. I don't think it's good to actually to use this as any kind of a general rule because it's not true. You'll notice that if there's only one rotation, let's suppose that we just have this first rotation by the angle psi, then if you go all the way back to the beginning, if you just look here at that first rotation, if that was my only rotation, then you'll see that psi dot times p3 gives me the angular velocity, and p, that basis p, would be my body because it's the only rotation. The other two rotations don't exist. So in that particular case, when there's just one single rotation about a fixed axis, in this case, when I say a fixed axis, I mean an axis fixed in the frame A, which is the original frame that I started with, which is this base reference frame, then I can say that the rate of change of psi is equal to omega 1, but that's only in that very special case, and that only happens in planar problems. And in general, we're not dealing with planar problems, so this doesn't apply in the general case. So the final result of this is we have 3 rotations, and those rotations are a 3-2-1 Euler angle sequence. So let's go back and summarize what we did here. So summary, which is that we defined, say it this way, a 3-2-1 Euler angle sequence which I called psi theta phi was defined. Using that definition, the 3 rotations were described, and then using those 3 rotations, we computed the angular velocity omega BA was determined in terms of the sequence psi, theta, and phi expressed, I should say and expressed, in the body fixed basis E equals E1, E2, E3. And that's the way you do Euler angles. Now, there are other Euler angle sequences that people sometimes use. In the Euler angle sequence that I gave you today, just to give you some sort of a feel for it, is what's called an aircraft Euler angle sequence. So the 3-2-1 sequence, 3-2-1 Euler angles, are often referred to as aircraft Euler angles. And the reason for that is to give you sort of a visual for an aircraft is that the way it works is that suppose that a you have a fuselage of an aircraft. And then you have the wings of the aircraft. Here are the wings of the aircraft. This is a very qualitative drawing, but it kind of gets the general idea across. Which is if these are the wings of the aircraft, and let's make the wings look a little bit better. So this is what's called forward, and then this direction is would be called right, and then the direction into the page would be called down. And the way this works is that the first rotation would be about the angle psi, about the down direction. So you first rotate, so rotation 1 is about down. And it's referred to as what's called the yaw angle. The second rotation is then you rotate and you do it about, so forward is x, right, we'll call that 1, right is 2, and then down is 3. So that's the rotation 1 is 3. We're doing 3, 2, 1, right? Then you rotate about 2, and that rotation is about the new right. The new right direction. And that angle is also what's known as the pitch angle. And then the third rotation, now you're going to rotate about the new forward direction. So once you do this, the first two rotations, now your aircraft has been yawed and pitched, and this is what's called yaw pitch. This is called the roll angle. So the sequence psi, theta, phi is also what's called yaw, pitch, and roll. That's the sequence, yaw, pitch, roll, aircraft Euler angles. And as I said, there are other Euler angle sequences that are used for, this is for aircraft. For spacecraft, there's a different set of Euler angles that are often used, which are called 3-1-3 Euler angles. There's also 1-2-3. There's 2-1-3. There's all different permutations of a three-angle sequence that can be used. But this is a very commonly used Euler angle sequence, which is why it was studied in this particular lecture. And we'll stop the lecture now because I'm giving you enough information. But just to complete this angle here again is psi, this angle here again is theta, and this angle is phi. So that's the end of this lecture, and we'll continue on with the study of more rigid body mechanics as we move forward.